To talk about the problem of detecting and diagnosing faults in our robot, because obviously, and I think everybody of us knows that we have some problems, we have some failures in robots. That's quite normal. So let me directly jump into the part and let me begin with motivation. So, what's the big picture of that problem? So, as I said, we have failures in our robots. And I'm quite sure that everybody of us has its own story about that. But still, I like to give you a very short clip that I think will emphasize that topic. Okay, that's again RoboCup in the year, I think, 2010 in Magdeburg. It was German Open. It was Stuttgart against us. And you'll see that, yeah, something went wrong. Just look at the audience, that's obviously that was not the thing that a robot should do in that situation. So that's definitely things we do not like to see in RoboCup. The question is, but what do we do about that? How can we prevent that situation? So one thing to go to for that problem is the architecture we proposed in the symposium in Eindhoven that gives you the frame for some recovery methods in your robot. What you see here is in the middle you see a recovery method, just a frame for it. On the left you see a robot system. And one point, I do not like to go into details of that part, is that you should have a clear separation of both. That's simply why we have already some existing robots, and the separation makes more easy to integrate that work, maybe in your robots as well. The second point that is very important here is that you do the recovery mechanism autonomously. So if you go back and see, just count the seconds, how long it takes from the occurrence of the failure to the impact, to the accident. And you will see that you have only some seconds left to prevent the robot suicide. That's only 4 seconds. 4 seconds, yeah. Now, how long does it take for you to press hard channel and stop the robot? I think more than 4 seconds. So. Therefore, we need some autonomous work here. I've modeled here a little decision cycle in the recovery method to is able to do that for you, or should be able. Next thing is, of course, we need some multi-robot support in that work. But only here for giving you the frame. What I like to concentrate in that talk is about the problem how we detect and diagnose some failures in our robot system. So, how do we do that? At first, of course, I'm not the only one who has that problem, and there's plenty of other paradigms out here. I like simply to give you some pointer to that paradigm. Maybe the most known is the model-based paradigm. Here, the white box approach here on the upper right side of the slide. And the core of that idea is that you have a dynamic model. So you really need to have a dynamic model that models your behavior of the component. That's the core. Then you give the input to your dynamic model. Your model gives you an output. You compare the outputs and get some residual out of that. If you have a big residual, it's a pointer that you should have a problem, like you have a problem with that. The problem with that approach is if you don't have a very good dynamic model, the results are not too good. The opposite to that is, of course, the black box model. So it's called the limit-based diagnosis. It's a very common one because it's a very easy one. You simply have your component, you have some observations on it, and you know out of empirical data that you have some range for the observations. If your observation violates that range, you assume your component has a problem. What I do with my approach is something in between. I call it the gray box, of course. And here I do not assume that I have complete knowledge about the dynamics of the component, but I do assume that I have at least some knowledge. So I call it cause-effect relations. That's simply the idea. If the component is in a failure, that's the cause, you should see some kind of observations, the effects. In that case, it's possible to have only incomplete knowledge about your observations. And you directly, obviously, because you have your causes directly modeled, you are directly able to infer a diagnostic result. How is it structured? So I like to start with a formal description of our problem. So the situation is, if we switch that, so the situation is you have a monitoring component that gives you some observation. So, okay, we have a set of observations. The observations are time variant. And you have a set of finite set of some possible fault types. And you have a set of the total state of your component. Is it okay or is it in a fault state? The problem now is how to find functions that maps the seen observation to the fault type and the state. That would be boring if you do not some constraints on that problem. Of course, the estimate should be as close to the real as possible. So let us constrain that a little bit more. So we are still talking about robots, you know. And a robot is a physical system, therefore you do not have complete knowledge about that. You always have to do some degrees of beliefs. So you do not have perfect knowledge. Therefore, I go for a formalism that is inherently able to model that, namely the probability theory. In that theory, the basic element in our problem description simply relates to some element, atomic element of the joint probability distribution. So namely the probability of a vector of observations, the state, and the vector of the fault types. In that sense, we can reformulate our problem to a conditional probability. The probability is simply what's, in the case of the detection problem, what's the probability of the state, let's say, okay, with given some observations. Yeah. And the next step is the next component. So it doesn't help really if we only have a probability. We like to do something about the fault. Therefore, we have to give the next component not only estimate or probability, no, we need facts. So therefore, we have to decide. Yeah? And that is done here in our approach with a maximum a posteriori decision. Simply, that formula just says, okay, we decide for the biggest probability for a random variable. Okay, now the formula, the approach is based on a joint distribution, and we do not do anything about it. We got something like that, a very complex structure. So the problem is now, how do we reduce the complexity of that structure? It's very simple. We do some assumptions. We model some knowledge about our domain. That means at first I assume that the component could be only in one fault type. That means if the component crashed, it's not possible that the same component is at the same time in the fault type deadlock. If I do that, you see our structure simplifies. The next thing is that the state of the component only relies on the fault type. So the state of the component is in the state okay only if we do not have any fault types or the fault type normal. If we do that, we get rid of some more dependencies in our structure. The last thing, or the last two things, are that the observations we see are direct or causal results of the fault type, and that the observations are independent to each other. If we do that, we lose another dependency. And I think that Bayesian network, that's what it's called, is much more efficient, much more easy to calculate than the one before. Now, we're not done. We still have forgotten one more thing. namely the things that we have time variation. We have still ignored the fact that we have to model somehow the time in that problem. Therefore, we have to extend that structure to a more dynamic structure, to dynamic Bayesian networks. If you do that, so at first, the dynamic Bayesian network is simply a Bayesian network replicated in time. So you have some discrete time slices in that problem, and you replicate your network for each discrete time slice. And for computational complexity, you assume that you have some time window that you work. The same as before, we have some assumptions now related to time. We assume the Markov sensor assumption that the observations in one time slice only depends on the fault type in that time slice. And the Markov assumption that the fault type only relies on the fault type of the last time slice. If you do that, we can model our fault diagnostic component like that. Here's the graphical representation of all the facts I have presented now. Here, the different time slices. Here's the replication of the Bayesian network. The last thing what we now have to do is we have to model the time connection between set instances. We do that simply with a transitional matrix that is modeled like that. So we simply have three types of elements in here. The first type is here, the failure of a fault type. What's the probability that the fault type stays, basically. The next is what's the probability, given that you are in a failure-free situation, what's the probability that you came to a failure? That's the key elements in it. And the opposite is what's the probability that you had a failure and recover from that failure. That's our components. So that's basically what we have. So you simply feed in your observations of the monitoring component and simply decide on the probabilities of the state and the fault type. If you do that like that, a very good question is how good does that perform? So some words on the experiment setup I've done. So that's some simulation setup on a software component or of more software components depicted in here. Here is the software components and simply the connections in between. What I've done as observations are, here's a very important thing, is only passive information. So that's only information what you can gather from your operating system. So that's something like CPU knowledge, the memory, the number of threads, and so on. I've modeled three types of faults: a deadlock, endless loop, and a crash, or an unpointed exception. And the state is obviously in the state okay or failure. The experiment was done like that. You are start in failure-free mode, you trigger a failure, you recover from the failure, trigger another failure, and so on. So let's see some plots and some numbers. What you see here is simply the probability of the output of the diagnostic component. I told you that we start in the failure-free mode, that obviously the fault type normal should be high, and you see it is high. Also the rest is very low. The space in between could be seen as the robustness of that component, of that approach. Simply the lowest probability of the right diagnosis to the highest of the wrong diagnosis. I've chosen that example because some very interesting fact happens here. In the time t bigger than 924, some disturbance happens. That was not intended by me, but it happens. And it's very interesting what the results look like. So you see that you don't see anything. Because there's still the right results here, even if one of the observations are wrong. You see here, the only effect is that your space in between decreases to some degree. So some more numbers. If you count the correct results versus the incorrect result, you end up with a probability or a percentage of over 96% of right detections. So that's after the detection, of course, after the MRP detection. Another interesting question is how fast is that? So what's the reactivity of that approach? I've simply calculated that time slice after the occurrence of the failure and got 10 seconds. Therefore, you have to know the update rate of the monitoring information was about 25 seconds. I say about 25 because we have adaptive monitoring here. I've done another experiment with some rule-based detection. It was a rule which was very sensitive to avoid wrong detections, false positives. And you end up with nearly twice the time. Okay, what have we seen? What have we reached now? I have modeled the problem of fault detection for diagnosis with a dynamic Bayesian network. Therefore, I got some robust estimates in respect to uncertainty and the lack of knowledge which we have in our systems. I found a very good representation of that problem by using Bayesian networks and including some knowledge about the domain. With a Bayesian network you can filter past results or even predict some, but not something. You got some good detection rates, I think, and you have a very low delay for the diagnosis. So thank you for your attention. Are there questions?
Yeah, a couple of questions, remarks. So this is basically a microphone.
Yeah, we can say like that, a Bayesian model is good.
No, you start from Bayesian model and for the assumption you're basically having a discrete state in the middle, so you have a microphone.
Yeah, it's both. I think you can see both as the same. So Markov model is already a Bayesian, dynamic Bayesian model. The dynamic Bayesian model.
Then, it's so long that it doesn't scale with the number of, in your case, failure states that you have. So it takes a rate of
maybe I have to put that too clear. You have some discrete failure states here, and you have to see, I do not a top-down approach, I do a bottom-up approach. So in your system, maybe you jump backwards, set the system, and you have one diagnostic approach per component in your robot. So if you have a vision component, you do the diagnosis only for the vision component. And after that, that's what I do next, is you try to combine that. You combine that with maybe your localization component and so on. If you combine that all, you can say how's the probability that your robot is still localized. Because the localization, I assume in that example, depends on the vision process. So you do that for every basic component in your robot. Does it clear?
Yeah, then I understand, but the clue there is the transition matrix.
Of course, yeah. Every
parameter depends 100% on
of course, you have to assume some probabilities on, let's say, the occurrence of some failures. But you can't do that if you go in the literature for reliability theory. You can estimate that out of some, I say, stupid numbers like lines of codes and so. But you can still assume a model here that depends on the time, how long you have tested your software, what's progress in the testing phase, and you can simply try to get a better estimate on that parameters.
So how did you get the numbers in your example?
In my example, I just assumed. Because
what were the numbers? What were the numbers that you put in the test?
If I could recall it right, I go for a number of 30% for failure. Let me switch. I go for a number of 30% for failure, and that you are in a correct state of 70. So, but in that case, the experiment was simply simulation experiment.
Yeah.
So I can put numbers at that. The only thing that changes that is how the time connection is done. So how far the new curve goes to the failure state or the normal state if you do not have any observations. If you have the case, as we have, that you have observations all the time. Your connections are still being updated all the time. And
Is this
so we have some dialogue here.
the example you were shown, the robot is running into the public. Is this system used to get more stable software, or are you still using that also during the game?
That's not more stable software. Now the software is for detecting problems in a running system.
Yeah, but if you have a running system, you can do a lot of testing and playing, but if I understood you correctly, you said it takes several seconds before it notices it. And in your example you gave, within 4 seconds it's going into the public.
But that scales with the update rate of your monitoring component. If your monitoring component is much faster. In my case, it was I get a monitoring update each 25 seconds in my simulation system.
Oh.
If your update rate is much higher, let's say 1 second, about below 1 second.
25 seconds. Okay.
It was just in the simulation system.
Yeah, okay.
But you got a detection.
That's why you,
10 seconds.
that's why you get 10 seconds.
Yeah,
Yeah, I was quite myself. 10 seconds is too long.
if you increase your update rate of your component, yes, yeah, the detection rate is much faster as well.
And it is still detecting also not only the software but also the individual components. Is my camera still looking correct? Is these kinds of things?
Yeah, so the software is for each component. If you talk about hardware,
Yeah.
that's another topic. Therefore, we have done a project that was about designing one board that measures some physical observations. See what's the current supply voltage of one board. If it drops down to 5 volt and you assume 12, obviously you have a problem. So that's the hardware monitoring tool you need to do exactly the same approach for your hardware component. So you can do that with, we've done that with voltages, we've done that with temperature, we've done that with even some sound. So the idea was if you shoot with your robot, you should hear some sound. If you don't detect that sound, your shooting device obviously doesn't work well.
Yeah.
And we have done, we can simply attach every sensor to that board and measure some physical values. You fit in that physical values in a model for your hardware component. In that case, you get the probability that the hardware model is okay on what board type that hardware model has. You combine that with the software drivers of the system and next software and that next software. After that, you got some estimate of, it's called in our case capability. What's the probability that the capability of the movement of the robot still works? That's the idea.
Okay, and you also talked about this detecting the white line, that then everything stops.
Detecting the white line?
And so because when he's running to the public, he most likely has to go over a white line.
Yeah,
Then
not
the
thought
whole
about
system
that.
goes on hold or something like that.
You have some problems because you have some white lines in the field as well.
Yes.
So you shouldn't stop if you cross the middle line.
It's very interesting.
Yeah, that's good. Normally hardware
Overly conservative.
maybe the topic is about detection. The problem hardware is about healing. If you can detect a fault, but sometimes you cannot heal the problem.
Yeah, but at least you
That
can
situation.
stop the robot not hitting the audience.
Yeah, I know.
If you
but
can't heal it,
the problem is, in some situations, maybe you are not able to stop it at all. Because of a short circuit transistor or something like that.
it's the robot.
It may happen.
Yeah, you should make sure that the robot is that it got a command, or if the self-healing method decides that the robot has to stop, it should stop. At least.
Should have some kind of device to
Yeah.
make sure that.
Yes.
So in a practical case, it could well be that one fault will cause the other. For instance, your example that a point that would lead to an endless loop, which would lead to deadlock or so. That would violate your assumption, right?
One fault, yeah, it's about fault regression of the system, I think. And a topic I haven't looked into too much right now. So, yeah, that's it. What happens if
So
you have...
you can use your fault definition such that you match your assumptions, but in a real practical case, it will very soon become too complex, I think. So perhaps you also have to find a way to deal with this fault regression.
Independent. Let's see, I've not thought too much about that. I think if you have, I'm talking about components. So, if a deadlock of one component, I think it's hard to progress to the next one.
It's a closed loop system. So an encoder can break, which can result in completely unstable robot behavior, because that is a closed loop.
And that's a controller. If the controller breaks, the component needs a controller. All the rest of the components still well defined, but they do not reach the hardware anymore.
Okay. Maybe we can think about good examples of this. And then the question, of course, is how it matches in your approach. It matches with your approach. So let's see if we can find some time.
Yeah, great. So, if there are no more questions, I think it's time for a break.
Yeah. So then we will go to lunch together now. I will pay for you. But